Okay, good morning. Today we're going to have a look at the second lesson of chapter 6. We're going to have a look at the equations and properties of planes. Okay, first of all, today's learning goals. After this lesson, you are expected to be able to understand the concepts related to the equations of planes in the 3D space. Express the equation of a plane using scalar equation, vector equation, and parametric equation interchangeably in 3D space. And determine the scalar equation of a plane given its normal vector. And last, solve problems related to the equations of planes in 3-dimensional space. Okay, first of all, let's have a look at the concept of scalar equation of a plane in 3D space. Okay, note that in 2 space, the equation x plus 2y minus 8 equals 0 defines a line passing through the points A, 0, 4, B, 2, 3, C, 4, 2, D, 6, 1, and E, 8, 0, as shown here on the graph on the top right. This same equation can be graphed in 3-dimensional space. Since there is a third coordinate z, right, in 3D space, each point will have a z coordinate associated with it. The 3D space version of this equation would be x plus 2y plus 0z equals 8. Since the z coefficient is 0, points such as a 0, 4z, b 2, 3z, C, 4, 2z, D, 6, 1z, and E, 8, 0z, where z can be any value, will satisfy the equation, right? Plotting sets of these points on isometric graph paper suggests a surface that is parallel to the z-axis and contains the line x plus 2y minus 8 equals 0. This surface is a plane, as shown here on the graph on bottom right. So in general, the scalar equation of a plane in 3-dimensional space can be given by ax plus by plus cz plus d equals 0, where uppercase A, B, C, D are all real numbers. Okay, so have a look at this concept here. Scalar equation of a plane in 3-dimensional space is given by ax plus by plus cz plus d equals 0. A, B, C, D are all real numbers. You have any questions? Okay, if you don't have any questions, let's consider an example here. Consider the plane defined by the scalar equation x plus 2y minus z minus 8 equals 0. We have just learned this can be a plane in 3-dimensional space, right? Can you determine if the point A, B, C are on the plane? Then determine the x, y, and z intercepts of that plane. Determine the coordinates of another point on the plane and write 2 vectors that are parallel to the plane. Okay, I'll give you 3 minutes to consider these questions. Then we'll have a look at the solution together. Okay, this checks your understanding of the scalar equation of a plane in 3-dimensional space. All right, let's have a look at the solution together. Okay, question A. If a point lies on the plane, its coordinates must satisfy the plane's equation, right? So we can insert the coordinates of 3 points into the equation of that plane. First, let's check point A. Left side equals 0. And right side also gives us 0, right? So left side equals right side. The coordinates of point A can satisfy the equation. Therefore, we know A is on the plane, right? If you check point B, substitute B's coordinates onto the left side of that equation. Left side equals 4. Right side equals 0. Therefore, left side does not equal the right side. So B is not on the plane. Then check point C. Left side equals 0. Right side equals 0. Left side equals right side. So the coordinates of point C can satisfy the equation of that plane. Therefore, C is on the plane. Any questions? Okay, that completes question A. Then question B, to find an intercept in 3 space, set the other coordinates equal to 0. For example, if you want to find the x coordinates, if you want to find the x-intercept, you must set the y and z coordinates equal 0, right? Okay, so following this method, we know first x plus 2 times 0 minus 8 equals 0. And that gives us x equals 8. So the x-intercept is 8 or 8, 0, 0, right? And to find y-intercept, set both the x and z coordinates equal 0. So that gives us y equals 4. So the y-intercept is 4 or 4 or 0, 4, 0. Then to find its z-intercept, we let both the x and y coordinates equal 0. And we can find z equals -8. Therefore, we know the z-intercept is -8 or 0, 0, -8, right? So rigorously speaking, x, y, and z intercepts are points. So a more appropriate way to write them is 8, 0, 0, 0, 4, 0, and 0, 0, -8, right? Okay, then let's consider question C. To find the coordinates of another point on the plane, you can actually choose any arbitrary values for 2 of the variables and solve for the third, right? For example, we can let x equals 1 and also y equals 1. And that gives us z equals -5. Therefore, 1, 1, -5 is a point on the plane. You can call this point D. Also, you can let x be 2 and y be 2 and solve for z, right? Choose any arbitrary points. Choose any arbitrary values for x and y, or xz or yz. Okay, again, the solution here is not unique. You might have a different solution here. And in question D, we know vector AC and vector CD are parallel to the plane, right? Because vector AC is 0, 3, 6, and vector CD is 0, -5, -10, which can both be expressed as a number times a vector 0, 1, 2, right? You understand? Also, the solution here are not unique. You might find 2 other parallel vectors parallel to the plane. Okay, do you have any questions? Any questions? Okay, if no questions, let's consider the next concept, which is a vector equation of a plane in 3 space. In 2 space, a line can be uniquely defined either by 2 points or by a direction vector and a point. In 3 space, more than one plane is possible, given 2 points or a direction vector and a point. To uniquely define a plane in 3 space, we need 3 non-collinear points or 2 non-parallel direction vectors and a point, right? As shown here in these figures. So now let's study the vector equation of a plane in 3-dimensional space. So the vector equation of a plane in 3-dimensional space can be given in this form. Vector r equals vector r naught plus t times vector a plus s times vector b. Or in other form, x, y, z equals x naught, y naught, z naught. That's the position vector of a given point on that plane, plus a real number t times a vector whose components are a1, a2, a3, plus another real number s times another vector whose components are b1, b2, b3, where r, whose components are x, y, z, is the position vector for any given point, for any point on the plane. And vector r naught, whose components are x naught, y naught, z naught, is a position vector for a known point on that plane. And vector A, whose components are A1, A2, A3, and vector B, whose components are B1, B2, B3, are non-parallel direction vectors parallel to that plane. And T and S are scalars, where T and S belongs to the real number set. So it's quite similar with the vector equation of a line in 3 space, right? The difference is that we have t times a vector plus s times another vector, and these 2 vectors are both parallel to that plane. So this concept is shown here in the graph on the bottom right. Any point on that plane can be expressed as a given point plus a real number times a parallel plus another real number times a parallel vector to that plane. So on the graph, the vectors r, r naught, t times a, and s times b form a closed loop. So algebraically, they can form an equation. R equals r naught plus t times a plus s times b. Starting from the origin, vector r naught goes to a known point on the plane. Then to 2 vectors in the plane that are scalar multiples of the direction vectors a and b. The resultant of these 3 vectors is the vector r, which is a position vector of any point on that plane. Okay, I'll give you some time to have a look at the concept here, okay? Okay, if you don't have any questions, let's have a look at the concept of parametric equations of a plane in 3 space. Remember that we have just talked about the vector equations, right? Which is x, y, z equals x naught, d naught, y naught, d naught, plus t times the first vector a1, a2, a3, s times the second vector b1, b2, b3. Then the corresponding parametric equations can be defined as x equals x naught plus t times a1 plus s times b1. Y equals y naught plus t times a2 plus s times b2. And z equals z naught plus t times a3 plus s times b3, where t and s belongs to the real number set. A1, A2, A3 are the 3 components of the first vector that is parallel to the plane. B1, B2, B3 are the second vector that is parallel to that plane. So A1, A2, A3 and B1, B2, B3 are non-parallel direction vectors. And the x naught, z naught, x naught, y naught, z naught is a position vector for a known point on that plane. Okay, do you have any questions? Okay, if you don't have any questions, let's consider a example, okay? That checks your understanding of the vector and parametric equations of a plane in 3-dimensional space. So let's consider the plane with direction vector A, B, and through the given point P naught. Write the vector and parametric equations of that plane. So this question is straightforward, right? If you know the given plane and 2 direction vectors that is not parallel with each other, you can directly write the vector and parametric equations of that plane. Second, determine if the point Q is on that plane. Then find the coordinates of 2 other points on that plane. Last, find the x-intercept of that plane. Okay, I'll give you 5 minutes to consider these questions, okay? Okay, now let's have a look at the solution together. Question A, a vector equation of that plane can be written as xyz equals 3, 7, 0. This is a position vector of a given point on that plane, right? Times a real number t times a vector 8, -5, 4. This is a vector parallel to that line. Times another real number s times 1, -3, -2. That's another non-parallel vector. That's another vector parallel to that plane, but not parallel to the previous vector. So the corresponding parametric equation for the plane can be given by x equals 3 plus 8 t plus s, y equals 7 minus 5t minus 3s, z equals 4t minus 2s. Okay, then let's consider question B. If the point -10, 8, -6 is on the plane, then there exists a single set of t and s values that can satisfy all of the three equations here, right? So we can try to solve this system. First of all, solve 1 and 2 for t and s using elimination. Two unknown quantities, two equations, that gives us a solution, right? So that gives us t equals -2 and s equals 3. So now let's check if t equals -2 and s equals 3 satisfy equation number 3 or not. You can substitute these two values into equation number 3 and then find right side equals -14, which is not equal to the left side, which is -6, right? Since the values for t and s do not satisfy equation number 3, the point -10, 8, -6 does not lie on the plane. You cannot find a single pair of s and t that satisfy all of the three equations. Therefore, that point is simply not on the plane. Do you understand? Can you follow me? Okay, then let's consider next one. To find other points on the plane, use vector equation and choose any values for the parameters and t and s, right? For example, you can let t equals 1 and s equals -1. Then in this case, you have the three components x, y, z equals 10, 5, 6. Or if you let t equals 2 and s equals 1, the three components are 20, -6, and 6. So we can find two other points, which are 10, 5, 6, and 20, -6, 6. Of course, you can also choose any values for the t and s to find some other points, right? Again, the solution here is not unique. You might have some other solutions. Okay, in question D, to find x-intercept, we can set the y and z coordinates be 0 and solve for s and t, right? That gives us t equals 7/11 and s equals 14/11. Then we can substitute t equals 7/11 and s equals 14/11 into equation number 1. That gives us x equals 103/11. Therefore, we know the x-intercept is 103/11 or 103/11, 0, 0. Okay, now do you have any questions? Any questions? All right, good. No questions. Let's consider another example. So consider this example here. Find the vector and parametric equations of each plane. First, the plane with x-intercept equals 2, y-intercept equals 4, and z-intercept equals 5. Question B, the plane containing the line x, y, z equals 0, 3, -5 times a plus t times 6, -2, -1, and parallel to the line x, y, z equals 1, 7, -4 plus s times 1, -3, 3. Okay, so let's consider question A first. I'll give you 3 minutes for question A, okay? Okay, now let's consider the first question together. Okay, so if you know the 3 intercepts, then you can find 2 direction vectors, right? You can simply use the difference between any 2 points. So for example, one of the direction vector is A, which is 2, 0, 0 minus 0, 4, 0, which gives us 2, negative 4, 0. And another direction vector that is parallel to this plane is 0, 0, 5 minus 0, 2, 0, which is 0, negative 5. Okay, again, the solution here is not unique. You might have some other solutions, right? For example, you can also use 0, 4, 0 minus 2, 0, 0, right? So for a point on the plane, we can choose either the x or y or z intercept, right? So for example, here I choose the x intercept. Sorry, the here we choose the x intercept, which is sorry, this should be 2, 0, 0, not 4, right? We can choose 2, 0, 0, which is the x intercept of this plane. So a possible vector equation of this plane is xyz equals 2, 0, 0 plus t times 2 times t times 2, negative 4, 0 plus k times 0, negative 2, 5, where tk belongs to the real number set. So this equation is not unique, like I said. You might have some other solutions, right? So different vectors equations could be written using different points to find the position and direction vectors. And if I have a vector equation like this, then the corresponding parametric equations are x equals 4, or this again should be 2 plus 2t. Let's correct this. Y equals negative 4t minus 2k. Z equals 5k, right? Okay, any questions? Okay, then let's have a look at the next question. The plane contains a line xyz equals 0, 3, negative 5 plus t times 6, negative 2, negative 1, right? So the point 0, 3, negative 5 is on the plane because simply that point is on the line. You can use 0, 3, negative 5, this vector as a position vector, which means the position vector of a given point, right? Since 6, negative 2, negative 1 is parallel to the plane, it can be used as a direction vector. The plane is also parallel to the line xyz equals 1, 7, negative 4 plus s times 1, negative 3, 3. Therefore, we can use the direction vector of this line 1, negative 3, 3 as a second direction vector for the plane. Since 6, negative 2, negative 1 is not a scalar multiple of 1, negative 3, 3, the direction vectors, so two direction vectors are not parallel, so we can use them to write the vector equations of that plane, right? So a vector equation of that plane can be given by xyz equals 0, 3, negative 5 plus k times 6, negative 2, negative 1 plus L times 1, negative 3, 3, where k and L belongs to the real number set. And the corresponding parametric equations for the plane are x equals 6k plus L, y equals 3, negative 2k, negative 3L. Z equals negative 5 minus k plus 3L, where k and L belongs to the real number set. Okay, now do you have any questions? So now you should be able to write the vector equation and parametric equation of the plane in three-dimensional space, okay? Okay, so now let's make a summary. The equations of a plane in three space can be written as a vector equation, a parametric equation, and a scalar equation, right? The vector equation of a plane in three space can be written as r equals r naught plus t times vector A plus s times vector B, or write in the components form. xyz equals x naught, y naught, z naught plus t times a1, a2, a3 plus s times b1, b2, b3, where r, the vector r equals xyz is position vector for any point on the plane. Vector r naught, whose components are x naught, y naught, and z naught, is a position vector for a known point on the plane. Vector A, whose components are A1, A2, A3, and vector B, whose components are B1, B2, B3, are non-parallel direction vectors, parallel to the plane. And T and S are scalars, where T and S belongs to the real number set. In parametric equations, x equals x0, x naught plus t times a1 times s b1. Y equals y naught plus t times a2 plus s times b2. Z equals z naught plus t times a3 plus s times b3. If you have a vector equation of a plane, then you can find the corresponding parametric equation, right? Okay, the scalar equation of a plane can be represented as ax plus by plus cz plus d equals 0, where the uppercase a, b, c, and d are coefficients. All of the 4 coefficients belong to the real number set. Okay, so there are 3 types of equations for a plane in 3 space. I hope you are able to write each of them using given information, okay? Do you have any questions? No? Okay, now, if you have no questions, let's have a look at another concept, which is to determine the scalar equation of a plane given its normal vector. Okay, first of all, let's have a look at the concept of normal vector. If we are given a vector n, whose components are a, b, and c, that is normal to a plane, which means perpendicular or orthogonal to a plane, and a point p naught whose components are x0, y0, z0, x naught, y naught, z naught on the plane, we can determine the scalar equation of the plane. So this situation is shown in this graph here. If the point P, X, Y, Z is any point on the plane, then vector P naught P is parallel to the plane, but perpendicular to the normal, right? So normal is represented using letter N, vector N. Okay, so vector P naught P equals XYZ minus X naught, Y naught, Z naught, which equals X minus X naught, Y minus Y naught, Z minus Z naught. That's the 3 components for vector P0P, right? Since P0P is perpendicular with the normal vector of this plane N, we know the dot product between P0P with the normal vector N is 0, right? Which means X minus X naught, Y minus Y naught, Z minus Z naught, dot product with A, B, C equals 0. So according to the definition of dot product, this gives us A times X minus X naught plus B times Y minus Y naught plus C times the difference between Z and Z naught equals 0. And then we can expand and rearrange the terms on the left. That gives us AX plus BY plus CZ plus negative AX naught minus BY naught minus CZ naught equals 0. So the expression in the brackets is made up of known values. So it is a constant, right? You see that? We can let letter D, uppercase D, to represent this constant. Therefore, we know AX plus BY plus CZ plus D equals 0 is the scalar equation of the plane, having normal vector N, whose components are A, B, and C. You understand? So basically, if you have a normal vector, you can express the scalar equation of that plane. Or if you have a scalar equation of a plane, you can directly find a normal vector of that plane. You understand? Okay, I'll give you 1 minute to have a look at this concept here. Okay, if you don't have any questions, let's consider a example to check your understanding of the property of this property here. Okay. So consider the plane that has normal vector n whose components are 3, -2, and 5, and contains the point P naught whose coordinates are 1, 2, -3. A, write the scalar equation of the plane. B is vector A whose components are 4, 1, -2, parallel to the plane. C is vector B normal to the plane. D, find another vector that is normal to the plane. Okay, I'll give you 5 minutes to consider these questions. All right, let's have a look at the solutions together. Okay, question A. Actually, there are two methods to complete that question. In method 1, we can use the dot product, right? So we can let P, X, Y, Z be any point on the plane. Then vector P naught P equals X minus 1, Y minus 2, Z plus 3 is a vector in this plane. Then the dot product between vector P0P and the normal vector N must be 0, right? Because normal vector is perpendicular to the plane. Thus, it's perpendicular to any line that contained in that plane. So that gives us 3x minus 2y plus 5z plus 16 equals 0. This is actually the scalar equation of that plane. Okay, in method 2, we know that if the normal vector of that plane is 3, -2, 5, then the plane can be expressed, the scalar equation of that plane can be expressed as 3x minus 2y plus 5z plus d equals 0, right? So first three coefficients corresponds to the components for the normal vector of that plane. Apparently, d is a undetermined coefficient, right? So in order to solve d, at least we need another point on the plane. So note here, P naught, whose coordinates 1, 2, -3, lies on the plane. Therefore, we can substitute its coordinates to find the coefficient d. So 3 times 1 minus 2 times 2 plus 5 times -3 plus d equals 0. That gives us d equals 16, right? Again, the solution is the same with the previous method. Scalar equation of that plane can be expressed as 3x minus 2y plus 5z plus 16 equals 0, right? You have any questions? Okay, good. Then let's consider second question. So in previous question, we have found the scalar equation, right? In second question, we know vector A is parallel to the plane only if the dot product between vector A and the normal vector is 0, right? You understand? Dot product is 0 means the two lines are parallel, right? Sorry, the two lines are perpendicular, right? If A is perpendicular to the normal vector, that means A is parallel to that plane. Okay, so the dot product between A and vector N is 4 times 3 plus 1 times -2 plus -2 times 5, which is 0, right? Therefore, we know vector A is parallel to that plane. Okay, in question C, we know that a vector is perpendicular to the plane only if it is parallel to its normal vector, which is equivalent to, it can be expressed as a scalar multiple of the normal vector n, right? Which means vector B must be able to be expressed as k times n, where k is a constant. So let's try to solve the system to find if there is any possible solution. That means 15, -10, 25 equals k times 3, -2, 5. So 15 equals 3k gives us k equals 5. -10 equals -2k gives us k equals 5. 25 equals 5k also gives us k equals 5. Therefore, when k is 5, B can be expressed as 5n, right? Clearly, in this case, vector B is parallel to the normal vector of this plane n. Therefore, B is also normal to the plane. Understand? Okay, question D. Find another vector that is normal to the plane. So any scalar multiple of the normal vector of the plane is also normal to that plane. The vectors 15, -10, 25. and 6, -4, 10 are two such vectors. Of course, the solutions here are not unique. You might have some other solutions, okay? As long as a scalar multiple of the normal vector, it's also a normal vector to the plane. Okay, do you have any questions here? Any questions? No? Okay, good. Then let's consider another example. This also checks your understanding of the property we have just learned, okay? Find the scalar equation of the plane containing the points A, whose coordinates are -3, -1, -2, point B, whose coordinates are 4, 6, 2, and point C, whose coordinates are 5, -4, and 1. Okay, I'll give you 3 minutes to consider these questions here. And then after that, we'll have a look at the solution together, okay? Slow. Okay, now let's have a look at the solution. So first, we can find a normal vector to the plane, right? We know vector AB equals 7, 7, 4. And vector AC is 8, -3, -3. Sorry, 8, -3, +3. These are two vectors in the plane, right? And we also know the cross product between vector AB and vector AC will give a vector normal to the plane, right? That's the definition of the cross product. So first we can find the cross product between 7, 7, 4 and 8, -3, 3. You can use a method shown on the right to find this cross product. And the resultant vector is 33, 11, -77. Thus, the normal vector to this plane can be 33, 11, and -77. Of course, more conveniently, you can use 3, 1, -7, right? Because 33, 11, -77 can be expressed as 11 times 3, 1, -7, right? So these two vectors have the same direction, and the only difference is the magnitude. So we can also use a simpler one, which is a 3, 1, -7 as a scalar, as the normal vector to that plane. So if you know the normal vector of that plane, you know the scalar equation of that plane can be expressed as 3x plus y minus 7z plus d equals 0. Of course, d is unknown to us, right? In order to solve d, you need at least one point. Either A or B or C. You could use either any one. So use one of the given points, such as A, to determine the coefficient D. So put the coordinates of A into that equation. That gives us D equals -4, right? Therefore, we know the scalar equation of this plane is 3x plus y minus 7z minus 4 equals 0. Okay, do you have any questions? Any questions? No? All right, then let's consider another example question. Use properties of plane to write equations. Determine the scalar equation of each plane below. In question A, a plane that is parallel to the xz plane through the point -7, 8, 9. In question B, there's a plane containing the line xyz equals 1, 2, 4 plus d times 4, 1, 11, and perpendicular to another line xyz equals 4, 15, 8 plus s times 2, 3, -1. Okay, let's consider question A first. I'll give you 3 minutes to have a look at that equation, okay? Okay, now let's have a look at the solution to question A. So we know the xy plane has a normal vector perpendicular to both x and y axis, right? One possible normal vector is the unit vector j, whose components are 0, 1, 0. Thus, the scalar equation will have the form 0x plus 1 y plus 0 z plus d equals 0, right? Or simply y plus d equals 0. Also, we know one point, -7, 8, 9 is on the plane. So we substitute the coordinates of this point into that equation. That gives us d equals -8. Therefore, we know the scalar equation of the desired plane should be y minus 8 equals 0. You have any questions? Any questions? No? Okay, then let's consider question B. Okay, again, I'll give you 3 minutes to have a look at that by yourself first. A plane contains one line and perpendicular to another line. Can you find its scalar equation? Contains one line means contains all the points on the line, right? Perpendicular to that line means we know the normal vector of that plane is actually the direction vector of that line, right? If you know the normal vector of a plane and also a given point on the plane, that's very easy to find a scalar equation, right? All right, let's have a look at the solution. Okay, in question B, if the plane is perpendicular to the line xyz equals 4, 15, 8 plus s times 2, 3, -11, -1, then we know the directional vector of this line is the normal vector to the plane, right? So the normal vector of that plane is 2, 3, -1. And the scalar equation has the form 2x plus 3y minus z plus d equals 0, right? The coefficients of x, y, z are the three components of the normal vector n. Of course, here we don't know the value for coefficient b yet. So you need another point on that plane to determine the value for d. So since the line xyz equals 1, 2, 4 plus t times 4, 1, 11 is contained in that plane. So every point of that line is contained in that plane, right? So we know the point 1, 2, 3, 1, 2, 4 must be on that plane because 1, 2, 4 is the position vector of a point on that line. So if a point is on that line, that point is also on that plane, right? So we can substitute these coordinates into the equation. And that gives us the value for D is -4. Therefore, we know the scalar equation of that plane is 2x plus 3y minus z minus 4 is equals 0. You have any questions? Any questions? No? Okay, so that summarizes our lesson for today. So before we leave, let's revisit today's learning goals. Make sure you're able to understand the concepts related to the equations of planes in the 3 space. Then express the equation of a plane using scalar equation, vector equation, and parametric equations interchangeably in 3-dimensional space. Next, determine the scalar equation of a plane given its normal vector. Last, solve problems related to the equations of planes in 3-dimensional space. Okay, last, please remember to complete today's homework and submit them onto Google Classroom before the deadline, okay?